Now that we have looked at the introductory ideas of dynamics, specifically what forces are, the difference between weight and mass, and what the net force is and what the normal force is, let's take a look at some of the sample problem. First, sample problem number 1. We're asked to find the weight of the following object. Again, a reminder, weight and mass are not the same thing. In part A, our object has a mass of 10 kilograms. To find the weight, it's simply using the formula Fg equals mg. Simply enough, 10 kilograms times 9.8, that works out to 98.0 newtons. Why 98.0 newtons? Specifically, it's because of its 3 sig figs. Same thing applies for part B, but this time we have a 50 kilogram mass. Well, with 50 kilograms, the weight is going to be significantly larger, which is 490 newtons. Question 2. What would be the magnitude and direction of the normal force acting on each mass in question 1 if they were sitting on a flat surface? Include a free body diagram. So in these cases, if the object is sitting on a surface, the net force has to be 0. And the reason being is that the object is not sinking into the table or floating away. So if the object is in what's called a static equilibrium, where it's not moving, the forces have to balance out. Well, in part A, we knew that the weight of the object was 98 newtons, so it makes sense that the normal force should be equal to that amount, but in the opposite direction. And when we take a look at the diagram, it makes sense that that would be the case. The normal force is acting up, the force of gravity is acting down. They are equal but opposite to each other, which means that they would cancel each other out, which explains this statement here. We know that the net force is equal to the sum of the normal force plus the force of gravity. Well, these two forces have to cancel each other out, otherwise the box would move. So we know that the positive normal force minus the magnitude of the weight should add up to 0. So when we bring the force of gravity to the other side, we have the weight, or the force of gravity, is equal to the normal force, which in this case equals 98 newtons, but 98 newtons up. The same can be applied for part B. The exact same mathematics are involved, same algebra, but the normal force is 490 newtons up. Now let's take a look at sample problem number 3. In this question, we're asked to find the net force that an object is experiencing based on the following circumstances. You're also required to draw a free body diagram. Again, as best practices, it's good to use GRFS to solve most of your problems, and you should get into the habit of using GRFS even when you're doing your homework. So let's consider part A. So we have our first force, which is 20 newtons north, and our second force, which is 40 newtons south. In both cases, these vectors are collinear, which makes the problem fairly easy to solve. So I've decided to label the first force FA and the second force FB. So FA is 20 newtons north, FB is 40 newtons south. Drawing the free body diagram. The free body diagram has to represent the magnitudes accurately. So as you can see, my second vector, FB, is about twice as long as my FA. Technically, they should be exactly twice as long. But when you're just sketching a free body diagram, you really just want to get it close. So to solve for the net force, we have to use vector addition. So we know that Fnet is equal to FA plus FB. In this case, Fnet is equal to positive FA minus FB, plus FA minus FB. Positive is because it is moving up, negative because it is pushing down. So if you notice, we are just substituting the magnitudes in because I've already actually put the directions in front. So it's just the magnitude of FA and the magnitude of FB. The result is negative 20 newtons or 20 newtons south as a vector. Part B. In part B, we have 3 vectors, FA, FB, FC, which are 15 newtons up, 30 newtons down, and 35 newtons up. These vectors are also collinear, which means that we can use straight vector addition. So when we take a look at the free body diagram, if you notice, the cumulative vectors in the upward direction are larger than the single vector that is in the downward direction. So you would expect this object to accelerate upward. So Fnet is equal to FA plus FB plus FC. Dropping the vector notation, Fnet is equal to plus FA minus FB plus FC. The positive means up, the negative meaning down. Substituting in, we have plus 15 minus 30 plus 35, which gives us a magnitude of positive 20 newtons, or F net is equal to 20 newtons up. Let's take a look at 3C. 3C, things are a bit different. And here's the thing to note. The vectors are not collinear. So since they are not collinear, we cannot use simple vector addition and subtraction. We have to use vector addition and subtraction, taking into consideration the direction. So let's take a look at FA. FA is 100 newtons north, FB is 40 newtons to the west. When we draw the free body diagram, it looks something like this. Magnitude of FA is larger than the magnitude of FB. Now, notice this. We have to find F net. The vector equation is still F net is equal to FA plus FB, but the key thing is they are not collinear, which means we have to be very, very careful when we are solving these problems that we solve them using the vectors. So, of course, next up is we need to draw the vector diagram. We draw our vector diagram, and you always start off with FA. FA first, followed by FB. The two vectors add up to F net. Next, we have to find the magnitude of F net. Finding the magnitude of F net, in this case, since it is a right-angled triangle, we can simply use Pythagorean theorem easily enough. So making that correction there, the magnitude of F net is equal to the magnitude of FA squared plus the magnitude of FB squared. Substituting our values in, that's going to be the square root of 100 squared plus 40 squared, which is equal to 107.7 newtons. The next step is to find the angle theta. Since, again, it's a right-angled triangle, we can use SOHCAHTOA. Specifically, in this case, we're going to be using tangent. Now, we had the option of using tangent or sine or cosine, but the reason why we chose tangent is because we know the values for FB and FA explicitly. However, F net has potential error in it because of rounding. So we want to avoid using the hypotenuse in this case, so it makes sense to use the opposite side, which is FB, and the adjacent side, which is FA, and that's why tan was the method of choice. Isolating, first of all, for theta, of course, because we have to do everything algebraically. We have to take the arctangent on both sides, so tan inverse or arctan of FB over FA, substituting in, that gives us an angle of 21.80 degrees. Therefore, F net is equal to 107.7 newtons north, 21.80 degrees west. And the reason why it's north and 21.80 degrees west, because if you take a look at the angle here, we are north, then west. So this angle here moves from the north towards the west, and that is the direction of our net force. And finally, for sample problem D. So in this case, in sample problem D, we have two vectors again, but they are not collinear, but even worse, this vector is not playing nicely. So when we have a vector question where the vectors are not collinear, and the resultant triangle is not going to be right-angled triangle, we have the options of using sine law and cosine law or using component method. In this particular case, I chose to use component method, and you'll see why. First of all, let's take a look at the free body diagram. So when we draw the free body diagram, I have FA to the west, and I have FB acting east 30 degrees north. If you notice, I have drawn in my compass rose in this amber color. And that's important when the vectors are not collinear and not playing nicely. I denoted the direction of FB as theta B specifically here. Next, the vector equation, again, is the same as it is before. It's just FA plus FB. What changes is the geometry. So when we look at the vector diagram, it's FA plus FB, and that's equal to our resultant, which is Fn. So in this case, we have to choose a different method. We can't use Pythagorean theorem. We do have the option, however, of using cosine law to solve this. And the reason why we're using cosine law is because we have the following. We know a side, an angle, and a side. So two sides and a contained angle. And that's how we know that we are going to be using cosine law to find the magnitude of F net. So the magnitude of F net is equal to the square root of FA squared plus FB squared minus 2 FA FB cos theta B. And all that is just cosine law rearranged and with using different notation. So instead of the letters C, A, and B, we're using F net, FA, and FB. When we substitute our values in, we get a magnitude of 28.3 newtons. So the net force is 28.3 newtons, but we also need a direction, which is why we have to find theta n. The little n stands for the net force. In this case, I've chosen to use sine law. Well, why have I chosen to use sine law? Sine law is the easier of the two, but sine law does run the risk of giving you an obtuse angle potentially. But in this case, we are totally safe. And the reason why we're totally safe is because our theta n, which is the angle that we're looking for, is not opposite to the longest side. The magnitude of FB is 30, and the magnitude of FA is 50. The only side that has the potential to be obtuse is this angle right here. So the next step is we need to isolate for theta n. Well, first step is we have to take FB and bring it to the other side. Since FB is in the denominator here, that is equivalent to division. The opposite of division is multiplication. Next step, we need to remove sine. Well, the opposite of sine is arc sine. So we need to take the arc sine of both sides, which gives me sine inverse or arc sine of bracket FB sine theta B over F net. Substituting our values in, we end up getting an angle of 32 degrees. Therefore, F net is equal to 28.3 newtons. 28.3 newtons is the magnitude. West 32 degrees north is the direction. And if we take a look over here on the diagram, we can see that F net is 32 degrees north of this west line, or west rotate 32 degrees north.